We are asked when 5 times 10 to the 22 molecules of ammonia react with 4 times 10 to the 22 molecules of oxygen, how many grams of nitrogen are produced? And we're given this reaction. So this is a limiting reactant problem because it's asking how many grams are produced. So whenever you see something like this, think, okay, this is limiting reactant because that determines how much product I'm gaining. And the second major point about this problem is that we always need to check if our equation is balanced. That trips people up on exams because if you're given an equation, you may think they've definitely balanced it for me and do the problem perfectly, but your answer is wrong. So just looking at this really quickly, we have 2 nitrogens on our right-hand side, 1 on our left. We know we have to balance this. And people balance equations in many different ways, some by inspection, some algebraically. I always check to see if I can do it by inspection first because doing it algebraically takes quite a bit of time. So just to do it by inspection, I usually start with a chart so I know how many of each species I have on my left and right hand side. So initially filling it in, we have 1 nitrogen on our left hand side, 2 on our right. And with hydrogen, we have 3 and 2, and oxygen, we have 2 on our left, 1 on our right. Okay, so now we're ready to balance everything. And there's a couple different things you should consider when thinking about what you're balancing first, what you're balancing last. So I balance the elements first that are not hydrogen and oxygen because usually those 2 species are present in a lot of different compounds in your equation and will be harder to balance. And looking at this O2 we have here, that's really easy to stick a stoichiometric coefficient right in front and not manipulate how much nitrogen and hydrogen we have. So I'm going to wait until the end to balance oxygen. And that's my thought process of how I figure out what I'm going to balance first. So let's start to balance. So first I'm going to balance N, or nitrogen. And I'm going to do that by adding a stoichiometric coefficient of 2 in front of my ammonia. And I always keep updating my chart so I know I now have 2 nitrogens on the left and right and I'm balanced. Now I will balance hydrogen. And I have to update how many hydrogens I have on my left-hand side because of this 2 I put in front of ammonia. So now I actually have 6 on my right-hand side. And so to balance hydrogen, I am going to add a coefficient of 3 in front of my water. So now we have 6 on both sides. And that looks balanced. So to balance oxygen, let's first update our chart. We now have 3 on our right-hand side. And this is a trick that I like to use a lot, and some people get tripped up by it. So if you don't like it, definitely keep going about balancing how you usually do it. But especially when you're trying to go fast in exams, I really like using this trick. So I'll write out what I'm going to do and then explain it. So I know that I want 3 oxygens on each side to balance. And I have 2 here. So if I put a 3/2 coefficient in front, I'm just saying I have 3/2 of 2 oxygens because this is O2. So these 2 cancel and I have 3 oxygen molecules. So if you're going to use this trick, you can't have any fractions in your final equation. So always remember to multiply by 2 so you don't have fractions. So if I multiply this entire equation we have by 2 to get rid of the fractions, I'm going to get this final equation. And sorry, I forgot to update this. We now have 3 oxygens on this side too. Okay. So we can go back, update our chart again. We now have 4 nitrogens on each side, but we're still balanced. And for hydrogen, we now have 12 on each side. And for oxygen, we have 6 on each side. So now we can move on to finding the limiting reactant. So within this step, the first thing I'm going to do is convert molecules to moles. And I think it's really helpful to always think about converting to moles. And that's because a lot of the time you use stoichiometric coefficients in your equation, in your balanced equation, to convert from one species to another. So I'm just going to do this using Avogadro's number. So I have 5 times 10 to the 22nd ammonia molecules. And I know that for every 1 mole of ammonia, I have 6.022 times 10 to the 23rd molecules. And I'm going to get that we have 0.083 moles of ammonia. And I'm just going to quickly do the same thing with oxygen. Using Avogadro's number. And I get that we have 0.066 moles of oxygen. Okay. So, similar to balancing equations, people find the limiting reactant in a lot of different ways. Something that I think is an easier way of doing it is to choose one reactant to convert to the other. And I'll explain once I've done this. So you can pick either one. I'll pick oxygen. So I have 0.066 moles of oxygen. And I'm going to convert this to ammonia, my other reactant, just by the stoichiometric coefficients of our balanced equation. Because we know for every 3 moles of oxygen we have 4 moles of ammonia. So that means in order to use up all 0.066 moles of our oxygen, we are going to need 0.0886 moles of ammonia. So if we look at what we actually have, which is 0.083, we don't actually have enough moles of ammonia to fully react oxygen. And because we don't, we know that ammonia must be limiting. So now that we know that, we can finally figure out how many grams of nitrogen we're producing. And we can just do that similarly by using conversions. So we're going to take 0.083 moles of ammonia, and we're always going to start with our limiting reactant. Once we know what it is, we're going to start with it to find how much of something's produced. So we can use the fact that for every 4 moles of ammonia, we produce 2 moles of nitrogen. And that's just based on our balanced equation. And then because our answer is in grams, or we need our answer to be in grams, we are just going to use the fact that 1 mole of N2 contains 28 grams of N2. And definitely this is something to be careful about, because some people will put, oh, this is 14 grams of nitrogen, but this is diatomic. So our answer is going to be that we produce 1.16 grams of nitrogen.